So let's say that we have all right. So first things first, what should I do? Again, we're looking for those key features with the possibility of graphing this at the end. Rita? Okay, how do I factor something with 4 terms like that? It's an Algebra 2 question. Hopefully we remember. If not, I'll remind you. It's not a big deal. Yeah, you want to use factor by grouping. That's exactly right. So just writing this off to the side. So you'd do something like that. The important piece is remembering that there has to be a plus sign in the middle of your 2 groups. So even though I had a subtraction symbol there, I just wrote as plus and negative and everything is fine. I can take a greatest common factor from the first group and a greatest common factor from the second group. That leaves these 2 pieces as also a greatest common factor. So when I pull that out, I get something like this. And I notice the x squared minus 1 is also factorable. That's a difference of 2 squares. Everybody's cool with remembering that factoring trick? So when you have 4 terms like that, that's your kind of go-to. If that does not work, in this case, if I gotten like an x plus 3 and x plus 2, then you'd have to go back to trying to do like that synthetic division stuff that you did in Algebra 2, which Barfaroni like takes forever. It's kind of time consuming. But I would not expect that to happen here. All right, so nothing reduces. So my vertical asymptote is just going to be at x equals 0. No removable discontinuities. My zeros would be at -3, +1, and -1. My y-intercept doesn't exist. Why not? Because x can't equal 0. That's where the vertical asymptote is. Yup, good. And then the last piece are those other asymptotes. So here I notice the degree of the numerator is 3. The degree of the denominator is 1. So I'd have to do a polynomial division here. How do I do that polynomial division? Oh, dude, it's easier than that. This is like the easiest stuff that ever easied because my denominator is a single term. It's a monomial. So I can just rewrite that as like x cubed over x plus 3x squared over x minus x over x plus or minus 3 over x. Right, I'm just going to write as 4 things with a common denominator. Totally fine to do that. And then I can reduce 3 of those terms. This piece then is the quotient. So that's my asymptote. It's actually like a quadratic asymptote, which is kind of weird, but hey, okay. Everybody's all right still? Okay. You could synthetic divide that, but like you'd have to use like a 0, I think, which is kind of weird. Anyways. I would not. I think what we did there is is the easiest way to kind of approach that. All right, so let's draw in some of this stuff. So I have that. How am I going to graph this quadratic? Rita? Yeah, so I'm going to need the vertex along with at least a point on either side of the vertex to at least get some semblance of a shape. How to find the vertex of a parabola? Yeah. So we still remembered that from a chapter or two ago when that came up rather frequently. So in this case, that's going to be -3/2. When I plug that in, what do I get there? I'm going to, well, I guess what would it be? It'd be 9/4 minus 9/2, so that's -9/4. Minus 1 is going to be -13/4, or -3.25. We okay with that? And then I'm going to pick two other points. So the way I like to do this is I'm going to pick them symmetric to the vertex. So I'm going to pick, say, x equals 0 and x equals -3. Now, the reason I'm going to pick them symmetrically like that, that's my choice. I don't have to do that. Well, plugging 0 in is really easy. I just get the y-intercept. And because of the fact that these quadratics are symmetric about their vertex, if I pick the x's symmetrically, the y-coordinate should match up, and it saves me the hassle of having to plug another thing in. Now, it's not that big of a hassle. You pick any numbers you want, as long as you got one on either side, and you're going to be okay. But, work smarter, not harder. You know what I'm saying? All right. So let's plug some stuff in here then. Oops, black. All right, so -1.5 and -3.25, and then 0, -1, and -3, -1. So there's my asymptote. Okay, let's start filling in the other pieces now. So -3, 0, -1, 0, and then +1. So the piece in here I can see quite clearly has to kind of look like that, right? It's the only way I'm going to be able to connect those two pieces. Is that okay? Over here now, I need to, oops, what am I doing wrong here, guys? I shouldn't be crossing that vertical asymptote, right? Sorry. And then here, I know that if to connect this and follow the asymptote, really have to come from the bottom. Otherwise, I'd be crossing that quadratic asymptote. So I know I really have to be kind of coming from the bottom to go through that other 0. And that ought to do it. Why is there nothing else over here? Because this little end keeps going to the left and up forever. So I don't need anything else over there. That end of the graph is just going to continue going to the left forever. So it's got everything on that side of the graph. That's it. That's my whole dooley-doo. This was kind of nice because I didn't even have to get out the calculator to try to calculate one of these limits. I could kind of infer from where the asymptotes were and where the x-intercepts were what this thing had to look like. So that was nice. That's like as tough as they would get, is something like that, where you have to like get that quadratic asymptote in there. But even that was not terrible, right? Should have felt fairly familiar to things that you had done algebraically. The picture is unusual looking, but otherwise this should look kind of like things we've seen before. At least the steps along the way, right? Rita.
Will you ever have to do like long division for
yeah, I might not have been any in the homework. It's certainly like, could you have to? Yes. In the homework, did you have to? No, I think everything could be done using synthetic division, which is fine, right? Like, that's the way I'd like it. It's way easier. So let's not worry about it until it kind of comes up, and we can go through it again if we need to. But it's one of those things like, did you get the same out of it? If the point of it is to do this stuff, do I need to do it? Yeah. Make it like the most tedious way possible to like get to the part that you need? Like, let's not. Let's just not, right? Like, it doesn't really add anything. All right. Moving on. So the next thing up is going to be solving rational equations. So let's talk about the methods that we have to do this. So one way, if you just have one fraction equal to one fraction, that's technically considered a proportion. How did you solve a proportion way back in geometry? You dealt with them all the time when you had like similar figures. Cross multiplication, right? Note that cross multiplication is only a solving technique. It's not actually how you multiply fractions. It's a technique to solve a proportion. Everybody's cool with that? Okay. So assuming that you have one or more fraction equal to one or more fraction, what can we do there? Make a common denominator. Add fractions, and doing so you've created a proportion. So then you could cross multiply. You could make a common denominator and then drop the denominators and solve the numerators equal to each other. Everybody's okay with that idea? And my preferred method, the method that I would use in all situations regardless, would be multiply both sides by the least common denominator. I call this clearing fractions. By multiplying both sides of the equation by the least common denominator, all the denominators are going to cancel out, and we'll just be left with a polynomial. And here, making sure that you're using the least common denominator is quite important. It's very easy to use just some other common denominator. If you do that, though, you'll probably end up getting like a degree 4 or 5 polynomial that's just going to be a nightmare, having to like do your synthetic division junk to try to solve it. Where if you use the least common denominator, things should work out much nicer, right? Polynomials get much harder to solve the bigger the degree gets. If we can keep the degree as small as possible, it makes the solving much easier. In all of these situations, though, there is one additional step that needs to happen even after you've done the solving that's described here. Does anybody remember what thing you have to do before you finish solving a rational equation? So you've got some answer. What do you still need to do with that answer? Yeah, you have to check for what's called an extraneous solution. What we mean there is does that solution make a zero denominator, right? So if one of the denominators in my problem was x minus 2, and when I solve the whole problem, I get an answer of 2, that answer doesn't count because it actually doesn't solve the original problem. It just makes the original problem undefined. So that one doesn't count. You have to throw it out, and you just keep whatever you have left, and if you don't have anything left, you just say no solution. All right. At this point, we're just going to run some examples of increasing complexity, starting with something like quite simple and ending with things that are, a bit more on the complicated side. Again, I'm going to say for the record, I am always going to use the clearing fractions technique on all the stuff I show you. You're welcome to use any of these other techniques. It's not wrong to do so. I think that this is the easiest technique overall. It works well in all situations. This is my preferred method. I think it makes life the easiest. But you're entitled to do, like, right is right. You don't have to do it the same way I'm doing it. Any of these methods I've described are fine. They're acceptable. They work. And in some contexts, may make life even easier than clearing fractions. But I think in general, this is the easiest technique overall, kind of in all situations. All right, so I have x plus 3 over x equals 4. If I look at what would the least common denominator be here if I look at all 3 of these fractions? Just x, right? Since the other denominators are all 1s. So I'm just going to multiply both sides by x. That gives me the polynomial x squared plus 3 equals 4x. What kind of polynomial is this? Quadratic. How do you solve a quadratic polynomial? It's got to equal 0, and then we could either factor or use the quadratic formula, right? Either would be acceptable. This one factors, so let's go ahead and factor it. So just factors to x minus 1 and x minus 3. The solutions we get are 1 and 3. The only denominator I have is x. If I plug 1 or 3 in, neither one would give us a 0 denominator. So both those answers are good. How do you guys feel on that? Pretty easy one, right? Not a big deal. So here, let's say we have x minus 6 over x plus 1 equals 0. Again, I have just one actual denominator, not counting the ones. I know there's ones there, but like they don't count worth a hill of beans, so I'm not going to worry about them. So I'm just going to multiply both sides by the x plus 1. So that's going to give me x squared plus x minus 6 equals 0. Again, I can solve this then by factoring or using the quadratic formula. I'm going to factor this because once again I see something that factors quite nicely. So my solutions are negative 3 and 2. Again, I have to check to make sure I don't get a 0 denominator. Neither one of those give me a 0 denominator, so they're both acceptable. No big deal so far, right? Everybody's happy? Remember doing this last year? Let's look at one that's a bit more complicated. Or I would say a little bit more course level rather than these first couple examples that were quite straightforward. So first thing I'm going to do is figure out what the least common denominator is. Here it's a little bit more complicated because I have 3 actual denominators. What's the first thing I should do to figure out the least common denominator? Factor, right? Ideally, I want them in factored form. Makes it much, much easier to see what's going on. And also, I should say at this step, I would also check to see if I can do any reducing. Because if I can do any reducing here, that also is going to make that least common denominator potentially smaller and the problem much simpler. Now, there's no reducing for me to do here in any of these fractions, right? But it's worth just taking a second and checking. Because oftentimes, if you can catch that, it makes the problem enormously simpler. Or can make the problem enormously simpler. Okay. What would the least common denominator here be then? X minus 1 times x minus 3. Excellent. Okay. So when I distribute that through to the left-hand side, I'm going to get 2x times x minus 3 plus 1 times x minus 1 equals 2. Everybody okay with how I did that? The reducing that happened. I didn't write any of it down because, again, at this level, seeing this a second time, I hope that that's okay. But if you don't understand where that came from, speak up and I can elaborate and show some more intermediate work. But my suspicion is that it's fine. If it's not, though, you're more than welcome to say something. We can elaborate. Okay, very good. So I'm just going to FOIL everything out, or distribute everything out and combine some like terms. Okay? So again, we're left with a quadratic here. The choices would be to factor, use the quadratic formula. What do you notice is a complication here?
Coefficient.
The leading coefficient of 2, right, makes the factoring kind of a hassle. As a result, I would choose to use the quadratic formula here. It's much more difficult to look at it instantly, see if it factors and how it's going to factor. If the leading coefficient isn't 1, I would say it's going to be about the same amount of work to factor as it would be to use the quadratic formula. I would just use the quadratic formula here. It is factorable, for the record, and maybe you see it right away, and if you do, that's fine, right? But I wouldn't worry about, like, how do you do that factoring again? Like, if you don't see it, guess and check. I would just use the quadratic formula in this case, because it's going to be just about the same amount of time. And the nice part about the quadratic formula is you're guaranteed to get a solution, right? Sometimes these are tricky to look at ones with the leading coefficient and tell if it is even factorable or not. You could spend a bunch of time trying to factor it and be like, oh, I guess I have to go back and use the quadratic formula anyways. All right. So 5 squared is 25 plus 4 times 6 is 24. 24 plus 25 is 49. So that's going to be -7 plus or minus, or sorry, -5 plus or minus 7 over 4. So if I add it, I'm going to end up with 2 over 4, or 1/2. And if I subtract, I'm going to end up with 5 minus 7. That's -12 over 4, -3. Right. Oh, yeah, thank you. So that just changes that to -0.5 then, and that to +3. Thank you. Appreciate you not letting me get too far before catching my mistake. Woo! All right. Again, go back and check. Where we're checking is in the original problem. If I plug -1/2 in, none of that's not going to give us a 0 denominator anyway. But when I plug +3 in, that gives us a 0 denominator here as well as here. Doesn't really matter whether it happens 1 time, 2 times, 10 times. As soon as it happens once, what do we do with this? That's extraneous. Yeah, we can't cross it out and we ignore it. So far, so good. No big deal so far, right? We hopefully remember kind of doing this stuff last year. This tends to be something we spend a pretty good amount of time on because it's not an easy skill the first time you see it, or tends not to be anyways. Oops. Okay. So first things first, to find that least common denominator, I'm going to go ahead and factor the one piece that's factorable, or that's not prime anyways, I should say. So I see that the least common denominator is just going to be x minus 3 times x minus 1. Okay. So that's going to give me 2.5 times x minus 1 plus 0.5 times x minus 3 equals x squared. Now, I'm looking at this and I go, yuckarooski, look at these stupid decimals floating around here. You know what I'm going to do to make this a little bit easier? Anybody with a guess? I could do that, but I'm just going to multiply both sides by 2. That'll make everything integer, which I think makes life a little bit easier. What do you guys think to that? Now, do you have to do that? No. And if you just wanted to like keep everything there and end up using the quadratic formula with the decimal in it, no problem. This to me felt like it's going to make the problem a little bit easier, so I just went ahead and did it. But there's going to be really no downside to just not doing that. So get everything on one side now. And hey, what do you notice here? Everything has a coefficient, or all the coefficients are divisible by 2, so I'll just divide that 2 right back out. Hey, that's nice. And if I look at this guy, though, not factorable, right? I don't have 2 things that multiply to give me positive 4 and add to give me negative 3. That ain't going to happen. So I'm stuck having to use the quadratic formula here, which is fine. It's no big deal. We've already dusted that thing off and used it once before when we didn't actually have to. Here, we had to. There was no getting around it. So we have 3 plus or minus. 9 minus 16 is negative 7. What do you notice here? Yeah, if I have a negative under the radical, it creates an I. And usually at this point, we just would say like no real solutions. Is kind of the standard thing to say here. We don't often want to report imaginary solutions for these kinds of problems, but if you wanted to, there it is. But I think if you checked in the answer keys or whatever, I would have just said no real solution at that point. How's that feel? No big deal, right? There's not much add-on here to what you would have done in Algebra 2 last year. So let's do a story problem. All right. Here we have that Bill wants to fence off a rectangular pasture. All right, well, let's draw a picture on that. On these geometry story problems, I'm like drawing a picture. His pasture must be 500 square feet. So I know the area for that pasture has to be 500 square feet. How do I know that that was representing an area? Because it's feet squared. Exactly. Yep. And then it says, what is the smallest amount of fencing Bill needs? So my fencing is just going to be, like this, right? That's the same as the perimeter. So let's give this stuff a name. I'll call that length and width. And since I have an area, that's going to be, I know that area equals 500. Well, I got that by doing length times width. So what I really have here is kind of like a system of two equations, right? I'm just going to solve for L and W and then take those answers and plug them back into the perimeter formula to get an answer, to get my final. So what I'll do is I'm just going to take this and separate either L or W to the one side. For the sake of argument, I'm going to do L. So just divide both sides by W. And then I'll make a substitution here. So I have 2 times 500 over W plus 2W. Okay with that? So what I'm going to do then, since it's looking for a minimum value, I don't have a good way of like obtaining a minimum value algebraically. If you take calculus next year, you will learn a way to do that. But without calculus, there's not a good way of doing that for a rational function like this. So all I'm going to do is I'm just going to go to my calculator and type in what I got here. I'm just going to replace the W's with X's. And F is going to represent our like Y variable, our dependent variable. And I'll set a window here. The perimeter or the length of one of these things, I don't know, I'll go like do something silly like 0 to 500, right? Like tough to imagine the the length of one of these things being more than 500 long and 1 foot high or something. But the answer is probably in there somewhere. And then the Y is the total amount of fencing. So again, I'll go 0 to say 1,000 or something. Again, that's probably an overestimate. But if the length of one of these things is 500, you have 501, 501. So like 1,002 would be the perimeter for that. I'm just kind of guessing at like over guessing so that I see what I need to. And then I'll just hit graph. So down here is where the minimum occurs. That's what I'm interested in. To find that point specifically, I press second and trace. And which of these commands sounds like the one that I want? Minimum, shocking. To use the minimum command, the calculator is going to ask me for a left bound, a right bound, and a guess. So I'm going to move my cursor somewhere to the left of that, where that minimum is. Now the window I chose here with the words here kind of covers up what I'm looking for. So I'm just going to be looking at the coordinates. So as soon as I see that Y start to get bigger again, I can stop. But I'm just going to be pressing the left arrow looking at that Y coordinate. And as soon as I see it start getting bigger again, I know I can, like, oh, there we go, right? Like it got bigger again. So I'll press enter. Now it asks for a right bound. So I'm just going to keep pressing the right arrow until it's, there you go, that looks good. And a guess, it doesn't really matter as long as it's in between the range. So X is 22.36 and the perimeter is 89.44. What was that? I forget now. 2236. And the fencing then was 89 point, I forget now, 44. And these are just feet. How is that?
What mode? Is it supposed to be in degree?
Doesn't matter.
Okay.
2 times 500 over x plus 2x.
Oh, wait.
That's what I typed.
Oh, I messed up.
Oh, okay. That's a relief then. It's nothing wrong with the calculator, it's wrong with the operator. Ha 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 ha. All right. What do you guys think? So far, so good? I mean, I don't have another example queued up ready for it. We could look at these ones. I guess probably 34 is the one that's closest to that problem since it's a volume situation. Does that sound okay?
Yeah.
Has the added advantage of being an even where you don't have the answer to check against also, right?
Yeah.
So that sounds good to me. Okay. All right. Otto is trying to create a tin can to have a volume of 60 cubic centimeters. What is the least amount of tin that he can use? All right. So I'll just draw myself a little picture. Every tin can that I've seen is cylindrical, right? And I haven't seen any cans that are rectangular or something. So I know the volume there has to be 60 cubic centimeters. And the volume for a cylinder is the area of the base, so like pi r squared, times the height of the can. The least amount of tin used is surface area. So I remember the surface area for a cylinder is the area of the top and bottom plus the area of the sides, which was the perimeter of the circle, times the height. Elaine, are you okay so far? All right, so what I'm going to do is I'm going to now solve the volume equation to isolate either the R and or the H, and then plug that into the surface area equation, graph it, and find the minimum. Now, which one of those RH looks like the preferable one to isolate? Oh, I would go H. I don't have to take the square root if I do the H, right? Yeah. Then I don't have to worry about plus or minuses or any of that nonsense. So I'll do that, which then I'll plug into here. Oh, sorry, that was supposed to be an R there. And if you were so inclined, you could say, oh, look, I can do some reducing. Although if you type in your calculator, does it really matter if you reduce it or not? Not really, if all we're doing is sending this to our calculator anyways, but. All right, let's start typing this in. So we have 2 pi, and then I'll have x squared plus 2 times, and then we'll just do 60 over x. And then setting my window, well, shoot, I don't know what's a reasonable guess for what the radius of this thing is, but it's got to be pretty reasonably small. So I'll just go to like 10 or something, right? Because 10 squared already is 100, and that's way too big to fit the volume. So that's a good estimate. And y is the surface area. I don't know what the heck to do with that. I'm just going to guess like 200 or something. I don't really know. I don't have a good a good guess there for any reason. And then just hit graph and see if it did it. Good enough. So there's the minimum that I'm looking for. So second trace, minimum command. That was much easier, much more centered in my graph. So it's easy to see my cursor going from the left side. Oh, Boise. The left side of that to the right side of that. That looks good. Hit my guess. So there's the dimension. That's the radius. Is that 212. And the volume, or the surface area there would be 84. And these are centimeters. And this is really the answer. That's the answer. That's the part that I want. Does that feel okay, Elena?
Yeah.
Cool. I don't want to do anything past this point today. This feels like a good stopping point. Mostly because we've been really hustling a lot, and I feel like we're in an okay spot right now. And then everybody just needs to like chill out every once in a while. So you should now be able to do 25 up to 34. And we're just going to kind of stop here for today. So for Sunday, which is what date is Sundays? Sunday is the 23rd. So 1 through 24 will be due Sunday. This newest stuff won't be due until the week after, and we'll add on to this plus whatever stuff we do next week. Does that feel good to you guys? Okay. I'm still feel like I'm getting my school legs back under me after break, so let's not, we won't have to go push it today. Give everybody a chance to get caught up and have like a real weekend still. What do you guys say? Okay, cool.